Okay, we're going to run through a few pH questions from the Year 13 content, leading on to some of the more tricky buffer questions. First thing we need to remember is that square brackets equals concentration. Concentration is moles per decimeter cubed. It's better if you write that as moles per decimeter cubed, because it actually reminds you of the sum that you need to do later on in some of the calculations. The final thing is that pH equals minus the log of the H plus ion concentration. So basically pH is minus the log of how many moles of H plus ions you've got per litre. Okay. Let's look at this first question. So this is a fairly straightforward question. However, there is a little trap in there for you, and if you don't notice it, you're not going to be able to get all the marks. So the first thing that what they're asking you to do is calculate the pH of a solution, and it's saying that you've got 25 cc's of 0.05 molar hydrochloric acid, and then you add 100 cc's of the distilled water. They want you to calculate the pH of the new solution. Now, normally you might just jump in and go, okay, we've got a 0.085 molar solution of hydrochloric acid, so we'll just minus the log of that 0.085. However, because they've added the 100 mils of water, 100 cc's of water, that's going to alter the concentration. It's going to dilute it, so the concentration is going to go down, so therefore the pH is going to go up. So basically what you need to do is work out the number of moles you've got. So moles in solution is V times M over 1,000. So our V is 25 times the molarity is 0.085 over 1,000, and that should give you 2.125 times 10 to the minus 3. That's how many moles you've got. So you need to divide that by the 100 and the 25 cc's, but you need to convert that into decimeters cubed. So it's that divided by 0.125, and that should give you the molarity. So that would give you 0.017 molar. That sounds about right, because we've diluted it significantly. So we've gone from 25 to 125, so it's gone down by a factor of maybe 5. So we're going for 0.17, so we just minus the log of the 0.017, and that will give us an answer of 1.76955. However, you need to be aware that they wanted 2 decimal places, so we're going to go for 1.77. Okay, we're going to look at a quick acid dissociation expression before we move on to the next question. So basically you should know that when an acid dissociates, it's going to give us H plus ions and whatever we've got left, the basic part of the acid. Within equilibrium, obviously, we can go either way. For your expression, so for Ka, we take the products over the reactants, so it's concentration of H plus, concentration of X minus, over the original concentration. And in these questions, you're basically given enough information to work out the unknown. So you might want Ka, but they will give you enough information. They might give you the original concentration, or they will give you pH, and you have to work out the H plus ion concentration from that. Unless you're told otherwise, unless you're given direct instructions in the question, the H plus ion concentration and the X minus ion concentration are the same. So what you can actually what you can simplify this to is that it's going to be the H plus ion concentration squared over the original acid concentration. If you don't know how we've got from that to that, and you don't understand why these are going to be equivalent, unless you're told otherwise, so if you don't understand why these are going to be equivalent, you need to go back and read through your notes at the beginning of the chapter. So we go back to the question. This is a continuation of the first question. So we're going to write an expression for the acid dissociation constant for HX. So it's exactly the same as we've written down before. So this should be easy marks for you. Ka is going to be equal to H plus ion square brackets concentration, X minus concentration over the original acid concentration. Now we're going to use this to answer this question. It looks tricky on the face of it, but we're going to be able to use everything in the question to help us get the answer. So they want to know Ka, so we've got an unknown, and the unknown is going to be equal to the H plus ion concentration squared over the original acid concentration. So I'm going to move this up, and what we're going to do is we're going to be able to put in the original acid concentration, which was 0.085, and the H plus ion concentration squared. Now the H plus ion concentration we're going to have to work out from pH. They tell us that the pH is 2.79. So if we do an anti-log of minus 2.79, we should come out with, oh God, so we've got the pH of 2.79. If we do the anti-log of minus 2.79, that would give us the H plus ion concentration. Again, if you don't know how to do that, you need to go back and read through your notes. So by the time we've done that, we'll get a H plus ion concentration of 1.62 times 10 to the minus 3. Now remember that we can square that value to give us the value to go at the top here. So if we square that, we should come out with 2.63 times 10 to the minus 6. And we do our calculation, and we're going to look for the unknown, so it's just that divided by that, and we should come out with a value to three significant figures of 3.09 times 10 to the minus 5.
Okay, before we go on, we need to look at these ice tables, which you should be familiar with from year 12, because we use these extensively throughout the A-level course. So you would have seen these when trying to calculate Kc, and various other equations during the course. So the ice table gets its name from the idea that we consider initial number of moles, the change in the number of moles, and then what we end up with, or the number of moles at equilibrium. So I've used an example here of a very simple neutralization reaction where we've got HCl and NaOH producing NaCl and H2O, and the reactant ratios are 1 to 1 and then 1 to 1 in the product. So it's a 1 to 1 to 1 to 1 reaction ratio. So you may be given the number of moles of H plus ions, or you might have to calculate that, and if you calculate it, it's generally through V times M over 1,000. Either way, you'll be given that. So at the start, in the reaction vessel, when we've just got the acid, we've got 1.5 moles of H plus ions, and that's it. We don't have any OH minus ions at the start, and we don't have any salt. So they're both 0. Now the question would then suggest to you that you're going to add a certain volume of OH minus ions. So again, we calculate this probably using V times M over 1,000. So if we add 1.2 moles of OH minus ions, they've got to react, and they will react with the H plus ions in a 1-to-1 ratio, and they will produce the salt in a 1-to-1 ratio. So if we've got 1.2 moles of OH minus ions added, we will produce 1.2 moles of salt. To produce those 1.2 moles of salt from the 1.2 moles of OH minus ions, we must have used up or reacted it with 1.2 moles of the H plus ions. And then all we're left with is to determine how many moles were of H plus ions, OH minus ions and salt. We have the answers in the table. So we focus on the H plus ions first. We've got 1.5 moles of H plus ions. We react 1.2 moles of that, so we minus 1.2 and we're left with 0.3. The OH minus ions will cancel out because we don't have any of them left because the H plus ions were in excess. And the salt, we started with 0 and we end up with 1.2 because we produced 1.2 moles. And as I said before, the OH minus ions, we don't have any of them left over because they've all reacted. And the only thing we have left over is the excess H plus ions, which is 0.3 moles, and then the 1.2 moles of salt we produced. Anything else that you look at is just a variation on that sort of standard method. So we use a slightly more complicated calculation. So we've got an equation where we've got 2a plus 3b goes to 4c. But when we're considering everything, we just need to consider these reacting molar ratios, so the coefficients in front of the molecules. So we've got a 2 to 3 to 4 ratio. So again, you could be given, or you have to calculate that you've got 1 mole of A at the start, and then you would maybe given 2 moles of B, and right at the start, before anything's reacted, we've got 0 moles of C. Slightly different this time, we could have 0.75 moles of A at the end. So to go from 1 to 0.75, we must have used up 0.25 moles of A. If we've used up 0.25 moles of A, so 0.25 moles of A is reacted, it must have reacted with B, and it must have reacted with 1.5 times as many moles, because the ratio is 2 to 3, so it's a 1 to 1.5. So if we've used 0.25 moles of A, we must have used 1.5 times the amount of B, which is 0.375. Calculating the amount of salt is a little easier because we've got a 2 to 4 ratio, or a 1 to 2. So if we've used 0.25 moles of A, we must have produced 0.5 moles of C. And then the calculations are the same. So for B, we had a number of moles of 2. We've used up 0.375, so we're left with 1.625. For C, we start off with 0, and then we add 0.5 moles, so we end up with 0.5 moles. And that's important later on when we start looking at the past paper questions. You need to focus on the number of moles of acid and the number of moles of salt that you are left with when we look at these equations later.
Okay, so let's see how we're going to use this ice equation when we tackle this question. So basically we're looking to see if we can work out the pH of a solution when we mix a known quantity of a known molarity acid and a known quantity of a known molarity alkaline. And they're going to react, and whatever's in excess will determine the pH. So first thing we need to do is work out the initial number of moles. So the question does say that we've got 25 cc's of 0.62 nitric acid in a beaker. So to work out that, we need 25 times 0.62 over 1,000, and this will give us our H plus ion, so our initial H plus ion concentration, and that's going to be 0.0155. Then we need to work out the number of moles that we add of the OH minus ion. At the start we've got 0. For the salt, even though we don't really need to consider it, we'll do it anyway because it comes into play later. we've got 0 of the salt. But we add, later on, the hydroxide, we add 38.2 of 0.55. So we've got 38.2 times 0.55 over 1,000. So that's how much we add. So we're going to bring that down. So we will now, just move this up, we're going to add 0.02101. Because this is a 1-to-1-to-1, we're therefore going to try to compare the acid and the alkali. We've got more alkali, so the alkali is in excess, so we're going to end up, we're going to wipe out the H plus ions, so we're going to have none of them left, because we've got excess alkali, so all of those are going to react, and we're going to form plus 0.1015 moles of salt. And you only get 0.0155 moles of salt because the acid's the limiting factor. So now, to work out at the end, because we've got our initial, the change, and the end, or the equilibrium, which is going to be the end for this one, we need to work out. So we're going to lose that much, we're going to have 0 of that, because we've lost 0.0155. We're going to end up with 0.0155 moles of the salt. And the remainder of the alkali, the excess alkali, is simply the 0.02101 minus the 0.0155 that it's reacted with. So you should end up with 5.51 times 10 to the minus 3 moles of the hydroxide. Now, there's another stage now that we need to consider. So we're going to zip back up. That's how many moles we've got, and we've got to try and work out pH. That's how many moles, but we need to work out the concentration. So if we go back up and we look that we've got 25 cc's and also 38.2. So the concentration of the OH minus is 5.51 times 10 to the minus 3 divided by the 25 cc's and the 38.2, which would give us 0.0632 decimeters cubed. So that would give us our concentration for the OH minus ions of 0.087025. We know that the ionic product of water is 1 times 10 to the minus 14. They give you that at the start. And we know that that's going to be equal to our unknown, which is the H plus ion concentration, times 0.087025. So by the time we've rearranged this, we should come out with our unknown, which will be the H plus ion concentration. So that's going to be 1.0 times 10 to the minus 14 divided by 0.078025, and that would give us 1.149 times 10 to the minus 13. So that's our H plus ion concentration. If we do minus the log of that, we will get 12.933, whatever it is, but remember, it wants the answer to 2 decimal places, So we should go for 12.9